Hello and welcome to the fifth session in sorting and searching. Before we get down to discussing searching, which is what we're going to be learning today, I thought we would just do a recap of the sorts that we've learned so far by looking at a comparison between these different sorts. And so we have the bubble sort, as we know, performing half n squared minus n number of comparisons. The number of exchanges are 0 for best case meaning the data is already sorted. 3/4 n squared minus n for average. Average would mean the data is kind of sorted. 3/2 n squared minus n for the worst case, where the data is totally in the inverse order of the order we want. So if we want the data to be sorted in ascending order, the input data that we get is in descending order. Right? So that's the worst case. As a list becomes less ordered, the number of elements out of order approaches the number of comparisons. So that's the bubble sort. Talking about the selection sort, that too performs half n squared minus n number of comparisons. Although the number of comparisons is the same as for the bubble sort, the number of exchanges is far less for the selection sort. Okay, so selection sort better than bubble sort. Now coming to the insertion sort, the number of comparisons for the insertion sort is determined by how the list is initially ordered, which means that if the list or the data is sorted, number of comparisons is n minus 1, number of elements minus 1. If out of order, it is half n squared plus n minus 1. Important to note that for the worst case, that is where the data is totally out of order, insertion sort is as bad as bubble sort and selection sort in terms of execution time. Right? Note that all these, that is the insertion sort, selection sort, and the bubble sort, are called n squared sorts, right? Because they executed n squared time, meaning the time taken to execute is always a multiple of the square of the number of elements, right? But the insertion sort does have some advantages. It behaves naturally, which means that it works the least when the data is fully sorted. It works a little harder if the data is kind of sorted, and has to work the hardest if the data is totally out of order. It also leaves the order of equal keys unchanged, and we've discussed this earlier where we spoke about a mailing list, and the mailing list is sorted in terms of the primary key first, which is a zip code, and then you also have it sorted within last name. If you're getting a new record which has the same zip code as an existing record, right, then you don't want that records, or you don't want those records to be rearranged, right, just because they have equal zip codes, right? And insertion sort will help to maintain that order. Now coming to the shell sort. Execution time for the shell sort is proportional to n raised to 1.2 for sorting an n number of elements. And if we had to represent this graphically, then this would be something like this. You can see that the dashed line, which denotes the sort that takes n squared time, right, has execution time increasing exponentially as the number of elements increases. Whereas the sort that would take n raised to 1.2 time, right, denoted by the straight line, has a much better graph in terms of execution time. Now coming to the quick sort, the number of comparisons on average is n log n, which means that for 100 elements to be sorted, quick sort would require 200 comparisons. How did we get that? Remember that we can represent 100 or n equal to a raised to x or 10 raised to 2. Right? And then of course we have log 100 to the base 10 equal to 2. Okay? 100 multiplied by 2 would give us 200. And that completes a comparison of the different sorts. Now let's talk about searching. And searching in the real world is related to databases. Databases exist so that a user can locate a record using a unique key. But today we're going to talk about searching in terms of arrays, right? And there's only one method for finding information in an unsorted array, which is to look it up sequentially. That is, examine each element in the array looking for the one we want. There is another method for a sorted array, which we will see shortly. But having said that, there are search functions that are provided by the compilers in the standard library that we can use to sort data. But many of these are inefficient. Why? Because they are generalized, and so they would tend to create more overhead when dealing with larger and larger amounts of data, right? So we're going to look at searching methods that we can use. We have, of course, the sequential search, and then we have something called the binary search. The sequential search, as you would have figured out already, starts at the first element in the array, stops when the match is found, or at the end of the array, can be used on sorted data as well. Talking about the binary search, this works on sorted data. It is vastly superior as compared to sequential search. Why? Because it uses a divide and conquer approach. So let's look at how the binary search works. If we have an array, for example, something like this, and we're looking for the element that has the value 4. Using binary search, we first figure out the middle. Once we've got the middle, to find the number 4, the binary search will test the middle against that number. So 5 is greater than 4. Therefore, we can discard part of the array, right? The search then continues with the first half. Now, we find a new middle. Middle is now 3. We test that middle against the value we're looking for. 3 is less than 4, which means we can discard half of this array. And so we are left now with the second half, and that's how we will arrive at the element that we're looking for. Now that we've looked at this, let's go ahead and write code to see how the sequential search works as well as how the binary search works. With the binary search, we're going to use both code with recursion as well as code without recursion. Starting with the sequential search, hashtag include stdio.h, hashtag include stdlib.h, and then hashtag include stdbool.h. We're going to be using a Boolean type variable, int main, and we'll have our array int ar, and this is going to have sorted data. Then we have a num to find variable, which will essentially hold the value we're looking for in the array. Int len equal to size of ar divided by size of ar of 0. Right? Int counter, and then we have the loop for counter equal to 0, counter less than len, counter plus plus. And within this for loop, we say if ar of counter is equal to num to find, then break. Right? And out of this for loop, we just have a printf. Printf found %d at position %d, comma, ar of counter. So that will give us the value we're looking for, and counter will show us the position or the index at which it was found. And that's all. So now we can run this. And you see found 4 at position 3, which is correct, right? 0, 1, 2, and 3. So that's about the sequential search. Now let's write code for the binary search without using recursion. So we start a new file. And we need the same files, so we can just copy these 3 lines. And now that we have that, we can start our main function. Now we need the array as well, so we can just copy it from here. Okay, once we have that, int num to find, and I'm going to keep it at 4. And then we have int len, and you can copy that as well if you like. So len equal to size of ar divided by size of ar of 0. Okay, once that is done, now because we're using the binary search, we will need int low equal to 0 and high equal to len. Okay, because remember we're using the divide and conquer approach. We also need a mid, right, for the middle. And we'll have a bool found equal to 0. Right? Now, while low less than equal to high and not found. Right? That's the condition for the while loop to continue. Within the while loop, we'll calculate mid equal to low plus high divided by 2. Then check if num to find is less than ar of mid, then high equal to mid minus 1, right? Else, if num to find is greater than ar of mid, then low is equal to mid plus 1. Okay? Else found equal to true. Right? And break. So here we will need brackets. Right? And that completes that else. Okay, now out of this while, we'll check if found, then print found %d at position %d, right, comma, num to find, comma, mid, right? So I hope this is clear to you as to how this works. We need a bracket there. Right, let's run this now. And you can see found 4 at position 3. Okay, so this is how the binary search works without recursion. Now using recursion, for that we start a new file. And again, we need the same files that we need to include, so we just copy that. Okay, we also need a function here that we're going to call recursively, so int binary, and it's going to take int star ar, int num to find, int len, int start and int end. Okay, now int main, and we need the array, so again you can copy that from here. And then we'll have int num equal to 4, int len equal to, again, size of, and you can copy it from the previous file if you like, divided by size of ar of 0. Then we call the function binary, sending in the arguments ar, num, len, 0 for start, and len -1, which is the last index of this array, for end. Right? And then of course you can have your exit. You can put that in the previous programs as well, just to complete the program. Now int binary, and we'll have int star ar, comma, int num to find, comma, int len, comma, int start, and int end. And within this function we'll have some variables, so int low equal to start, high equal to end, and mid. Bool found equal to 0. And now we say if low less than equal to high, right, and not found. Within this if block, we say mid equal to low plus high divided by 2. If num to find less than ar of mid, then high equal to mid -1. Right? Else, if num to find is greater than ar of mid, then low equal to mid +1. Right? Else found equal to true. Now out of this if block, we'll check if not found. Then we'll call binary recursively, sending in the arguments ar, comma, num to find, comma, len, comma, low, comma, high. Right? So we may have a new start or a new end depending on these if statements. Else, printf found %d at index %d, comma, ar of mid, comma, mid. Okay, so now we run this and you see found 4 at index 3. Right, so that's how binary search works with recursion. So this ends our session for today and our module as well. In the next session, we will begin a new module. We will start with discussing the queue, and then in later sessions move on to the stack, linked lists, and binary trees. So till then, take care, stay safe. Bye.